Hello and welcome to the presentation of Q discharge-based emergency vehicle traffic signal preemption. My name is Vít, and in my talk you will learn about what traffic signal preemption is, how is it usually used nowadays, and how our solution helps. Finally, I will show you a video from our experiment campaign and also some simulations which are publicly available on GitHub. Consider the following situation. You can see a fire brigade truck going through the intersection controlled by traffic lights. Because the signals are red for the approach that the emergency vehicle is coming from, the truck needs to overtake other vehicles through the opposite direction. Even though the emergency vehicles can pass the intersection with blue lights and sirens, this is potentially a very dangerous situation. In fact, according to the study of almost 200 accidents involving emergency vehicles from Germany, about 1/3 of them happened while going through the red traffic lights. By now you can probably guess what preemption is. It is a way how to mitigate this problem by giving the right of way, in other words, green light, to the approach of the intersection from which the emergency vehicle is coming. That means the driver of the emergency vehicle can be sure that he will not be in danger and can go faster. Benefits of preemption are twofold: safety and improved response time. Nowadays, preemption is usually implemented as shown in the figure. When the emergency vehicle crosses some virtual border located in predefined distance from the intersection, it sends the signal via cellular network to the traffic lights controller. The controller, upon receiving the request, starts the preemption. Setting up the virtual border can look something like this. A traffic engineer needs to specify this kind of a shape in a map. Crossing the border by the emergency vehicle is then detected via GPS localization. This has some shortcomings. Firstly, the border shape must be specified for each intersection uniquely. This doesn't scale well in terms of engineering time and effort. Secondly, the preemption might be started too soon if the trigger distance is set too conservatively. Then it might also delay the other traffic. On the other hand, the trigger distance could be less than necessary in case of heavy traffic. If there are big queues of vehicles, the emergency vehicle might still get stuck in the traffic. This brings us to the goals of the proposed solution. We want the new preemption method to be easier to deploy to new intersection without manual settings of the trigger borders, and we want the trigger distance to be adjusted based on current traffic situation. You can see a schematic picture of the method. There is no virtual border now, and traffic light controller knows the number of vehicles standing before the stop line. The controller will use this information. The emergency vehicle sends messages directly to the controller and potentially other vehicles that can forward the message. Let me point out that we didn't deal with how to count the number of vehicles in the queue. We assume that this information is provided to the controller. Computer vision techniques can be used or some other estimation methods using stationary detectors. We also didn't deal with the details of setting the preemption traffic light phases. This is already handled by traffic light controller. The core of the paper is to compute the time when to initialize the preemption rather than how to do it. Generally speaking, similar methods appeared in the literature some time ago, but the way how we compute the trigger distance is novel. To explain the algorithm in more detail, let's think about the trivial case when there are no vehicles and the traffic light signal is red. We ask, when to set the signal to green. Imagine there is the emergency vehicle arriving at constant speed to the intersection. The emergency vehicle is periodically sending its position and speed to the controller via vehicle-to-infrastructure communication. From the position, the controller can determine the distance d between the emergency vehicle and the intersection stop line. Because the controller also knows the speed, it can compute the time of arrival. So, ideally, we would have the controller starting the green phase at the exact moment when the emergency vehicle reaches the stop line. Of course, in reality, we would put some safety time, so the green light is set a little bit sooner. So now, after receiving the beacon from the emergency vehicle, controller has the following policy. Start the preemption in TA, arrival time, minus the safety margin. Let's consider there are some vehicles standing in a queue. The computation from the previous slide stays, but now we need to compensate for the vehicles somehow. The traffic light controller knows the number of vehicles, which is n. Our aim is that the emergency vehicle joins the queue when all the vehicles are already going at some speed, which we call saturation speed. When the vehicles get green light, they start accelerating, one vehicle after another, with a little reaction delay of the drivers. We compute the time necessary for all vehicles, even the last one, to reach the saturation speed. This time is called TL. At time TL, since the start of green light, there might be a few moving vehicles left in front of the stop line. This is the trailing tail of the queue. We compute a correction term that compensates this as well. We call it TX. Notice that we don't compute when all the vehicles pass the intersection, but when they reach the saturation speed instead. The formula is now complete. Let's see how it looks like in the simulation. In this simple scenario, we have 20 vehicles queue up in front of the traffic light. At time 200, the emergency vehicle joins the scene, and when the time is right, requests preemption. The green light is set according to the computation from the algorithm. You can see that the emergency vehicle joins the queue when all the vehicles are already running at their saturation speed. You can see a time distance plot from this particular simulation. The vertical axis shows the distance to the intersection, which is itself located at distance 0.0. The horizontal axis shows the time. You can also see the coloring of the traffic light signal in time at the horizontal line. You can see the emergency vehicle join the queue of vehicles at the right moment, when all the vehicles were already going at their saturation speed. What remains to explain is how to compute TL and TX. We exploit the queue discharge model developed to describe the dynamics of vehicles at traffic lights. See the source for the details. This model allows us to see the speed, flow, and headway time as measured on the stop line of the intersection as a function of time since the start of green light. What you see is the fit of the model based on the simulations we used to develop the method. What is more important are the parameters derived from the queue discharge model. For time TL, we use average reaction of drivers, Tx, and average acceleration time needed to hit the saturation speed, Ta. Another value we are interested in is the average spacing of vehicles in maximal flow. Combining this with the dependence on the flow in time, we can approximate how many vehicles are still in front of the stop line and what is the distance of last vehicle to the stop line. This allows to compute the x. Computation of these parameters is described in the paper. You'll also find there a listing of actual identified values. What we didn't talk about yet is the case when the controller receives the beacon when the traffic light signal is green. This calls for additional branch in the algorithm. Please consult the paper for the details. You can see how can the final trigger distances look like at a real intersection. The area with blue border is the polygon currently used, the virtual border I spoke about earlier. In comparison, the numbers are trigger points for our solution based on the number of vehicles in the queue. You can see that our method basically shifts the trigger distance based on the queue size. We managed to do experiments in real traffic. Let's see the video from this particular intersection. In this experiment, we went in ordinary vehicle equipped with vehicle-to-infrastructure communication unit. We kept constant speed, 50 km per hour. In this first transit, as you see at the top right corner of the video, there was only one vehicle standing in front of the stop line. Because there is yet no way how to detect the number of vehicles, there was a person standing at the intersection, counting the vehicles for the approach we were going from, and uploading the count to the controller via smartphone application. You can see at this transit, a request was sent 240 meters up front, and if we were through emergency vehicle, we would have easy time passing through this intersection. At the second transit, there were 13 vehicles standing, and the request was sent 517 meters up front. On the top left corner, you can see the side view from the intersection. You can see that only our approach of the intersection has right of way now. By the time we reach the vehicles, they are already going at some speed, and we seamlessly join them. The emergency vehicle would easily go through this situation. You can see in the side view that the moment we pass the intersection, the opposite direction gets green light. The simulation you saw earlier is available on GitHub, as well as the simulations from the intersection where the real experiments took place. The simulations are implemented in Vane's framework, which combines well-known Sumo for traffic and Omnet++ for networking simulations. The ongoing traffic is set from real measurements collected from induction loops in the area. In conclusion, our method computes the time when to start preemption based on the model of the queue. It is a good trade-off between helping the emergency vehicle and delaying other traffic, because we compute only the minimal time necessary for queue to discharge. When more cameras are used to observe the traffic at intersections, this method will be easily deployable to new ones. As most preemptive methods, even ours is helpless in case of urban gridlocks, and it causes desynchronization of traffic lights. Our method also needs to set up the parameters of the model, which might be different for different types of intersections. Thank you for watching my presentation, and in case of questions or comments, feel free to contact me. Enjoy the conference!